What I would like to discuss in the following video is the use of an important analysis in food um, profiling. That is the use of lethality calculations as offered by Phoenix Temperature Measurement in its food monitoring system in the ThermalView food software package. Before we talk about the application of the calculation and the assumptions that are made in the calculation, how it's applied, and the values of it, it's probably worth us just summarizing the value of the calculation from a technology perspective. In food processing, obviously we're looking to cook our food to get not only the quality and the characteristics of the food that our consumer requires, but obviously a critical requirement is the safety of the food as defined by many of the HACCP regimes that are in place. To help with proving food safety, we can perform lethality calculations for the food process itself. Food processing, though, generally is separated or split into two separate categories. One is referred to as sterilization, and the other is pasteurization, which we're really going to focus on. Sterilization, as its name suggests, is a very harsh form of cooking, whereby you wish to kill all of the microorganisms in the product because there is no additional preservation of the product after the processing step. This generally applies to canned products, whereby the product itself will be sitting on a shelf in a supermarket or a shop with no freezing or chilling or additional preservation methods in place. For sterilization, we're targeting Clostridium botulinum, and we're looking to achieve a processing temperature of a minimum of 121.1 degrees for 3 minutes. And this is generally applied in technologies using steam retorts or pressurized cooking. Pasteurization, on the other hand, is a less severe form of cooking, and it's generally applied to ready-to-eat type products, whereby in addition to the cork, there will be additional preservation methods applied to the product to maintain shelf life and keep the product safe for duration of that shelf life period. Those preservation methods may involve things like controlling the pH, the water activity, salt levels, chilling, and even freezing. For pasteurization, when we're looking at the microorganisms of interest, they will vary from product to product, and the pasteurization conditions, i.e. the cook temperature, the time of cook, etc., required for that pasteurization will be governed by the product itself. If we take a typical example, though, of a standard poultry type cook process, the common microorganism that's used to study the cooking or the safety of the product would be Listeria monocytogenes, abbreviated to L mono if used later in the video. Under these circumstances, generally the pasteurization target conditions would be cooking to a core temperature of 70 degrees and maintaining that core temperature for a minimum of 2 minutes. That 70 degrees for 2 minutes is required because scientifically it's been proven that under those conditions we will reduce the population of microorganisms, L mono, in that product by a minimum of 6 log or 6 orders of magnitude. This would then deem the product to be safe for consumption. The maths associated with lethality is all based around proving statistically that the product has achieved a thermal cooking process conditions that will render it safe for consumption, because the microorganisms under those conditions are statistically going to be killed within the cook process. When we're talking about pasteurization as part of our lethality calculation, there are two abbreviations that are used, or two units. One is F0 or PU. Both are interchangeable. And these are describing the successful nature of the cook mathematically based on the temperature history of the product itself. Two critical parameters as part of that are the following. The decimal reduction time is the time required at a nominal cook temperature for a particular microorganism to be reduced in population by 1 log or 1 order of magnitude. So for instance, if I have a piece of chicken with a population of 1 million Listeria monocytogenes microorganisms in it, at that decimal reduction time, I will reduce the population at the reference temperature from 1 million to 100,000. 1 order of magnitude, or reducing the population by 90%. The PU, or the F0 value, then is measured in minutes, and this is the number of log reductions you require in your cook multiplied by the actual decimal reduction time it takes to reduce the population by 1 order of magnitude, or 1 log in the microorganism population. For Listeria monocytogenes, the decimal reduction time at 70 degrees is generally given as 0.26 minutes. So to achieve 6 log reduction, I'm going to need to multiply 6 by 0.26 minutes, which gives me 1.56 minutes. Interestingly, you'll see here that that is close to our 2 minutes, which is our defined nominal cook regime for chicken. So all we're doing is we're rounding up that temperature, that time of 1.56 minutes to 2 to give us a level of safety if you were to do a simple time at temperature calculation. So we have our pasteurization value. In order to perform the calculation in our temperature profile, there are a number of parameters that we need to have in place. So on this slide, you will see that at the top here, we have our reference temperature. This is the target core temperature we need for our cook. So not the oven temperature, but the actual temperature inside the product that we have cooking. So the reference temperature is the core temperature of the product we need to achieve. The process time is the actual amount of time that cook temperature is achieved to actually maintain or reduce the population of microorganisms in the sample that we're actually cooking. A critical parameter is the Z value. This is referred to as the killing rate. So this describes how, by changing the temperature of the core of the product, how effective the killing rate is, or the pasteurization is, of the product. On a simple level, if you increase the reference temperature or the core temperature of the product by the Z value, it will reduce the decimal reduction time by a factor of 10. So if our decimal reduction time is, for instance, 1 minute, if we increase the reference temperature by Z, that decimal reduction time will change from 1 minute to 0.1 minutes. The decimal reduction time, as I've said before, is the time necessary at the reference temperature to reduce the population of the microorganisms by 1 order of magnitude, 1 log, or 90%. Let us now move on to looking at how we can apply the calculation. I'm not going to go into detail about how the maths works. We can provide information on that if you require. There are some technical articles that have been written which fully describe how the mathematics is implemented. But what I want to simply do is to show you how easy it is to apply the principle of lethality calculations in the software. The important thing is that you need to have the necessary parameters that we've already reviewed and be confident that they apply to your cook regime. My recommendation is, if you do not know what they should be, consult advice from technical resources, academic press, and also consultants that work in the industry. At no point should you use parameters that you are not confident with that may or may not apply to the product or the processing that you are implementing in your cook or your cook monitoring. So if we look at the slide in front of us now, this is basically a dialog box taken from the Thermal View food software, and it relates to what we call the product library. In this product library file, we're basically describing how we're monitoring the cook regime. Here we have a double D oven with a single rack with a number of shelves on it. You can see here the ham joints that are on the shelves. The probe locations are positioned over that rack. In this library file, though, we can additionally apply our PU analysis parameters, linking them directly to the product that we are profiling. In this dialog, we can put all the necessary parameters we can put in, and we can actually generate a little library file here. We can have different microorganisms with different parameters if you've got different cook regimes you want to monitor. In this particular example, we've got our standard Listeria monocytogenes. We're doing the pasteurization calculations based on this microorganism, and therefore the parameters we're putting in for the calculation are the default conditions for that. So 70 degrees, our Z value is 7.5 degrees, our decimal reduction value in minutes is in fact 16.2 seconds. So this is, remember, the time it takes at 70 degrees to reduce the microorganism population by 1 order of magnitude. And we want to achieve a minimum of 6 log. Now 6 log will give us a time of a pasteurization value or an F0 value of 1.56 minutes, but we're going to round that up to give us a little bit of confidence to 2 minutes. So if we achieve a F0 value of 2 or more, we are guaranteeing that we have a log reduction of the microorganisms throughout the cook of more than 6 log. You can though choose what these conditions are against which you want to monitor your process. So what is the output from the software if we apply these parameters? In the Thermal View food software, in the analysis tab, and we'll show you this later on where I actually use the software live itself, we have our F0 button or our PU button depending on which unit you've selected. And this is the table that we then see for the PU calculation. We have our graph showing the core temperature of our chicken fillet going through a conveyorized linear cook process. And we have now a table. Now the table is split into 3 main sections. One is over the current zone. So for the process zoom that we have on our graph, what we are being provided with is a calculated F0 value in minutes, what that relates to as a decimal reduction value. So in this particular case, probe number 2, our F0 value is 222 minutes, which equates to a decimal reduction value of 823 or 824 if you round up. Now, if you want to, you can actually, because we put in our target F0 value of 2 minutes, the next part of the table will show us that the target F0 was achieved at this particular time in the process, at this particular temperature for each of the 4 thermocouples. If you wish, there is a cursor on the graph, and if you move that cursor across the actual profile itself, it will give you the summation of the F0 at that particular process position. That becomes very helpful because it allows you to determine in the process exactly when you're achieving your minimum F0 value, i.e. proving the safety. So you can, to a certain degree, start to optimize your process to see whether or not you can reduce either the cook temperature or maybe even increase the line speed of a conveyor to give you more efficiency. Here we have a summary of the parameters that we use for our calculation. And last but not least, there is a very helpful little graph that shows you the change of F0 with time. You see here there's a cursor. This position of the cursor matches the position of the cursor on the profile. So you can see exactly how the F0 value changes through the process for each of the individual thermocouples. So in practice, the application of the F0 or PU values in the thermal view food software is very simple. The interpretation of the data is also easy and effective. So what we can immediately do is show what the total F0 value is for your cook regime and what that means in terms of the decimal reductions. You can then see immediately whether or not you are exceeding your safe limits to prove not only the quality and the safety of your product, but by controlling the process using this parameter, you've got the most accurate and safe way of improving potentially your product yield and also your process productivity, your efficiency, your fuel saving, which may be critical to overall bottom line of your process. I will now go on and explain how the F0 and PU calculations can be used live in the software to hopefully show you how efficient and easy it is and the value of the information that it can provide to you. So let us now look into how the ThermalView food software works with the implementation of lethality calculations. So the use of pasteurization units or the calculation of pasteurization units or the F0 units as described in the previous theoretical video. On the screen at this present moment, we have a standard temperature profile for a chicken cook process. You'll see from the profile graph, we have 6 thermocouples, of which 5 are active. The red and the black traces are, as you can see, the air temperature being monitored in the cook, reaching a temperature of close to 180 degrees. And the other 3 thermocouples, probe 3, probe 4, and probe 5, are thermocouples inserted into the core of chicken portions that have been cooked in a linear conveyorized oven. If I go to the probe thermocouple location display, you can see a pictorial representation of the type of application we're talking about. It's not technically accurate because the positions may not reflect exactly where the thermocouples are, but it gives you a feel for how that is and a description of the probe locations. The graph will obviously show us the rise of temperature inside the chicken portion, but the question is, how do we calculate the pasteurization values for these 3 respective samples. If I want to set the pasteurization values up, I would first go to the product library file, which gives me a dialog box in which I can set up all the parameters to describe not only the probe locations as we saw in the location image previously, but it gives me the ability to set up the parameters necessary to calculate the PU analysis results. At the top here we have our microorganism of choice, Listeria, and we simply then put in the parameters to perform the calculation as we described in the theory section of the video. Our reference temperature for Listeria is 70 degrees. Our Z value is 7.5. The D value, or the decimal reduction value, if you remember, is the time necessary at 70 degrees to reduce the microorganism population by 1 order of magnitude, is 16.2. Now, for this particular process, we're looking for a minimum of 6 decimal reductions or 6 log reductions. So if we multiply 16.2 by 6, we get, I think, 1.56 minutes. And so what we're doing here is so our target pasteurization for safety is 1.56 minutes, but we're going to round that up to 2 minutes to give us a little bit of wiggle room around that. So 2 minutes, a pasteurization value of 2 minutes minimum would guarantee that we have a minimum of 6 log reduction of the Listeria monocytogenes population in our product during the cook, or the outcome of the cook process. Remember that 2 minutes at 70 is our general industry standard for chicken cook if you're not using the Listeria pasteurization calculation as part of your profiling. Let us now see how that reflects. We put our parameters in. I'm now going to go to the PU calculation tab of the analysis section. Let's scroll up a bit. Now, what we have in addition to the graph now is we have the calculated pasteurization values for the profile, but for different aspects of the profile itself. You can see here in the center part, we've got our PU analysis confirming what parameters are being used for the calculation. We want to check that we're applying the right numerical values. But what we're going to look at now is this table. Now, we have results for probes 1, 3, 4, 5, and 6. Now, you may wonder why at the moment over the current zoom, which is the graph that we're looking at on the screen, why we have these stars for probe 1 and probe 6. The reason for that is that obviously for lethality, we're not really interested in the air temperature. And because the air temperature is going up to 150 degrees and even higher, the actual pasteurization value that's calculated for this data is very large indeed. It doesn't really make any sense. The star indicates that we've got values exceeding 1 million. So we're going to exclude those from the calculation. So what I'm going to do is for focus, I'm going to turn probe 1 and probe 6 off, which are the two air probes. And we're going to focus now purely on the 3 product probes, 3, 4, and 5. So what the table is now telling us is the pasteurization value calculated for probes 1, 3, 4, and 5 over the zoom that we're looking at. If I was to zoom in, it would then change the conditions for the zoom I'm looking at. But I'm going to go back to profile zoom, changes, and I'm going to go back to full zoom now. So this is for all of the data I'm looking at. So we have a pasteurization value for channel 3 of 1064. Remember, for our particular requirements, we're looking for a target PU value of 2 minutes. So we're exceeding that significantly. It also calculates the actual number of decimal reductions that the profile is giving us, which is 3,940, which is in excess of anything we need to prove safety for our product. So you could argue that we're actually cooking the product far more than we need to achieve the safety. Remember, be careful that you are balancing product safety with obviously the requirements of the cook to give both the characteristics of the product, so the coloration, the browning, and also the tenderization of the meat, and making sure it is fit for consumer from a eating experience perspective. So that's over the current zoom. We can determine from the results table also when the target PU value of 2 minutes was actually achieved in the process. And it actually tells you how many minutes into the process did we achieve safety. So we've got 11 minutes, 7 minutes, and 10 minutes. And it also tells you what temperature on each of the 3 profiles that safety target was achieved. A very useful feature included in the table is the reporting of the pasteurization value at the cursor position. Notice on the graph there is a vertical cursor that I can move left and right. Now you'll notice that the cursor position will tell me what the temperature is for each of the 3 probes or 3 traces. It will also tell me what the pasteurization value is and also the number of decimal reductions. So I can actually see exactly for each of the 2 probes, if my target is 2 minutes, at this particular point here, I can see for probe 4, the orange probe, I've achieved a PU value of 2. So that's the point at which I've achieved product safety for that particular channel. Channel 1 and channel 3 and channel 5, sorry, they haven't quite achieved that. So I can actually see for them each in turn where I need to get to actually achieve my 2 minutes. Dragging it across, I can increase to, there we go, roughly about there. So for probe 5, that's the point at which I get my minimum lethality for probe 5. But at the same time, probe 3 is still under required PU value. If I go any higher, let me see where I can get probe 3. A little bit of manual adjustment. There we go. At this point here, so 11 minutes and 2 seconds into the process. So at that point, all of the probes, the product probes, have achieved my 2 minutes PU value or higher. So at that point, I know that I've got product safety. So as it stands, this profile, everything that is achieved in terms of cooking post this point in the process is giving added confidence to the safety of the product. But the question is, can that be reduced? If I can reduce that amount of time and still get the quality of the product I need from a eating experience, maybe I can increase the productivity or the efficiency of the line. Probably what you noticed was when I was moving the cursor on the main graph, in this bottom right hand corner, we have a graph of PU against time. So the cursor position, time reference on the graph profile and the PU graph are matching. So you can see from the PU graph what the PU value is at any point in the process graphically, which is a nice way of seeing how quickly the PU value changes as you move through the process. So you have full control over what you're looking at. So it's as simple as that. Let me just go back to the product library and remind you that this is where we set up the parameters. If you wanted to set up a new microorganism or a new process, you go to product new. So I'm going to say new microorganism. Click OK. I would then simply put in the values, reference temperature, Z value, decimal reduction value, and target value. Remember that those values are critical to the success of the calculation, and it's a significant important requirements to check that those values are appropriate for the process you're doing, the product you're profiling, and how it's formulated. For instance, the reference temperature, the Z value, and the D value will all be governed by things like the meat type, the preservation methods of water activity, pH, and other things that could affect the characteristics of the calculation. So if you need to ask for consultative help from your local providers in terms of food safety. So it's as simple as that to set up a new file, and that would then be added to the library, which you can call upon in the future. And to save that, you would simply press the finish button. It will save that information to the product library file that you've set up. So analysis of PU is very, very easy. And if you wish to, you can also go to a report and you can include the F0 results on that. So at the moment, I've got a full report selected. I'm going to go to current report or create report, and you'll hopefully see the results coming out. So I've got my report showing my 3 traces for the product. I've got my pasteurization table results, the probe location image, all fully documented in a fully certified and traceable report. So an easy way in which you can prove to your HACCP auditor or your internal quality team that your process is providing the safety it requires.